Hello, Assalamu alaikum. My name is Mohammad Ilyas and other two members, Amit Shah and Farhan Tanvir. We will present a paper for the course CIS 589 and our paper title is ISREG Empowering Real-Time Intelligent Optimization and Control in Network Next Generation Cellular Network. First, we have to know what is the ISREG. ISREG is actually the Edge Radio Intelligent Control, and it is a platform for deploying and managing their real-time radio control applications at the edge of 5G or Open RAN networks. It's a part of ongoing efforts to bring artificial intelligence and machine learning based intelligence to the RAN control, particularly in Open RAN architectures. So why the ASREC is used in this paper actually, we have to know it. Uh, so in the next generation cellular network, there are some challenges in the networks. So first challenge is radio access networks are becoming softwareized day by day. That's why they are more flexible and programmable. The second thing is RAN actually expose data collection and control interface where they wants to be so much smarter for controlling the network. And the third one is existing RAN intelligent controllers actually open work at slower time scales, which is greater than 15 millisecond latency, usually running in actually wireless network environments, which is too slow for the real-time radio controls. That's why this paper introduced a concept age reg. So first we have to know what is the actually purpose of age reg and why this age reg is needed. Because in the real-time decision making, we need sub-millisecond time scales for critical optimizing wireless performance, especially for the handling fast changing channel conditions, which is actually a wireless environment where the signals behavior varies fastly. And the second one is enabling low latency applications, where a lot of applications actually involved, like online gaming, video conferencing, autonomous vehicles, telesurgery, AR, VR applications, and industrial automations and robotics. And the third one is running AI-driven dynamic optimizations, where actually some real-time smart tuning systems using intelligence which is learned from the data. That's why this paper introduced this SREC actually. The solution of SREC is introduce some real-time radio intelligence controller, like it is co-located with the distributed unit in the network and close to the radio edge. And another advantage is it is actually decoupled from the RAN stack, so it can operate independently. The third one is sub-millisecond decision making, which is actually faster than cloud-based architecture. And we have to know what actually makes the ESREC special for these paper applications. First one is actually real-time AI in the loop. AI-based policies needs some context-aware control decisions. And the second one is micro applications where the custom real-time control program over ESREC actually needed. And the third one is system integration. Although this ESREC is decoupled from the RAN stack, but it behaves like it embedded in the RAN stack for the quick response. And the fourth is the superior performance, which is up to the 25% improvement in the throughput and the application performance compared to the model-based or slower control strategies. And the last one is outperforms cloud rig, which is significant and especially in the dynamic mobile environments. And we have to know actually what is the contribution of this SREC. The first contribution is a real-time radio intelligence controller designed for TTI level synchronization with the RAN stack, which is ensures that real-time telemetry, data collections, and AI-driven control without violating the TTI constraints. And it operates independently from the RAN stack while interfacing via Open RAN architecture. And another thing they actually include in this ASREC is ASREC emulator, which is another training module uh, which works in a cloud where they collect data for offline AI training, testing, and development. And it also supports trace-driven full-stack emulation, like allowing evaluation across multiple users and applications. That's why they improve some parameter in this actually applications, which is 5 to 10% higher throughputs for the real-time scheduling and near real-time process, and a 15% throughput gain with reinforcement learning based real-time scheduling, and a 30% quality of quality of experience improvement for video streaming like AI driven and application aware scheduling. And why they motivate for actually real-time radio intelligence controller. Actually, in the wireless network channels, which is work so faster. So in mobile scenarios like drones and cars, channel quality changes every 3 to 4 milliseconds. That's why even in low mobility situations like indoor robots, changes happen less than 10 milliseconds. If we consider these two applications, then there is a option needed which actually work for sub-millisecond TTI level control. And uh, second one is why the real-time and non-real-time control needed. Actually, real-time control increases the throughput, like 1 millisecond latency compared to the cloud-based near real-time rate, which is 30 millisecond latency. This experiment shows 33% performance drop in throughput with near real time due to the delayed decisions. And why the AI training needs no latency? Because the reinforcement learning works better when the state action reward feedback is actually real time. So if we consider 60 millisecond delay in the non-real time situation, the training is less effective than that's why the performance is a little bit lower. That's why they actually introduced this SREC as a motivation for the radio intelligent controller, which is actually critical for RAN functions like beamforming, interference management, and MCS selection, and all the required real-time AI in the loop only possible through an edge deployed REC like SREC. And we have to actually know why they actually saying the SREC is the best one from among the actually radio intelligent controller, because if we consider the other frameworks like Scope, Coloran, Oren E2, FlexRAN, and FlexRig, they actually focus on near real-time control, which is 10 to 30 millisecond latency, which is often used for RAN slicing and resource allocation using different type of applications. This type of actually framework has some limitations, like they are actually lack true real-time execution, and some also cannot handle AI training and inference under the tight latency. There's another architecture if we consider CS, ARM, and ORAN DFs. They actually can fulfill the time scales, but they still operate in near real-time domains. Among the frameworks which is existing in the field, the Janus is the best one they consider, but this framework also attempts real-time radio intelligent controller, but it is actually tightly integrated into each vendor distributed units, which is making it vendor specific and less flexible. That's why they introduced this edge. Then we have to know what is the difference between other framework and this edge. There are some advantage in edge. The first advantage is it is fully decoupled from the RAN stack, which is using in the Open RAN architectures. So it works actually different types of vendors platforms. And the second advantage is built on the open source tools like HRS RAN, which is actually softwareized radio system for 4G and 5G mobile network development and testing. And the another one is ZIM interface, which is actually is a standard of interface for developing and testing reinforcement learning algorithm, making it accessible and easily trainable for the actually artificial intelligence or reinforcement learning. The third advantage of SREC is supports real-time policy execution like less than 1 millisecond, while training happens offline in the non-real-time situations. The fourth advantage of SREC is it enables robust AI control at TTI level, which is validated through the over-the-air interface in mobile communication. The media streaming research AI shows that the freer work actually focus for artificial intelligence for video bitrate control from the server side. But this edge rack uniquely allows network side real-time AI control, which is offering cross-layer optimization for better quality of experience. In this actually table, we can see the difference between different types of actually framework where they actually show the connectivity to the RAN stack. If we see the FlexRay, LoRaWAN, and the DFs, they are three frameworks. They are actually disintegrated. But the Janus is integrated and the ESREC is also de-integrated. So we can consider out of 5 frameworks, ESREC can fulfill these integrated requirements for the connectivity to the RAN stack. And if we consider the monitor and control, they before 3 frameworks, they actually work between 10 millisecond to 1 millisecond. But for the ESREC, it actually works less than 1 millisecond. If we consider the application awareness, so all the requirements like adaptability to channel fluctuation for the AI training support with real traces and the other options, all the requirements can be fulfilled by the SREC. So I have finished my part. The next part will continue my actually group member Farhan Tanvir.
Sorry, I will continue for the next part.
Okay, okay,
So,
thanks.
hi, Professor. This is Amit. Um, Let me explain the HREC concept architecture, and I will walk you through this diagram. On the left side, we have the cloud part of the system. Here you see the cloud data center, which includes the application server and the cloud RNN intelligent controllers. These controllers run two types of apps: is XApps, RApps. We accept which work in near real time, and RApps is which work in the non-real time. These apps help monitor and optimize the network from the higher level. Below that, you can see the ORN concepts components. These are the OCU, ODU, and the ORU. The ODU includes layer like RLC, MAC, and IPHY that handles radio communications. On the right side, we have the main focus, the real-time edge rig. This is located at the edge and does real-time decision making. Inside the edge rig, we have a Redis database to store fast access data, a policy exclusion block that runs UApps or micro apps, and a real-time metrics monitoring platform to collect network data. The UApps here are key. They can control network functions like resource allocation or uh, beamforming instantly based on what's happening right now. There's also an OpenAI gem wrapper here. It allows training and testing UAPs using AI models before deploying them in the real-time network. At the very bottom, you will see the UE or user equipment, like mobile phones, like mobile phones. Sorry, data flows between the network and the UE. The HRIC helps keep everything optimized in the real time. So overall, this architecture shows how edge concepts, cloud and edge components together making real-time intelligent decision for the modern network. Okay. Okay. So it's now let's look at the design goals behind the edge rig. The first goal is real-time intelligence. Unlike traditional controllers that rely on the cloud data, uh, edge rig uses local edge data. This helps this uh, this helps it make decisions almost instantly within 1 millisecond. The second design is the edge and cloud teamwork. The edge rig acts fast using the edge data, but can also send that data to the cloud for deeper analysis. The cloud can then help improve decision making over the time. The third goal is modularity. The edge rig follows open standards, especially for the ORM. That means developers can build and update apps easily, and it can work across different hardware from the different vendors. These design choices make edge rig flexible, fast, and future ready. Uh, okay. So finally, let's talk about the real-time exclusion module. This module is where the actual control happens in real time. It runs the UAPs that control different RN functions like beamforming or scheduling. It connects both the RN and to the cloud. Developers can build these UAPs using tools like OpenAI, which is great for the reinforcement learning. These apps use real-time data stored in memory with tools like Redis. The great part is these UFs start simple and then improve over the time they get more feedback and training from the cloud. This allows Azure to get smarter and more effective without disrupting the real-time performance. In short, the real-time exclusion module is the heart of the H3, it keeping the network smart and responsive.
Hello, I am Farhan Tanvir. Now I am discuss the talk about the rest of the slide. Now I have been here discuss the edge simulation module. Basically, the uh, this slide is talk about the real-time execution module of edge RIC. It's run a small app called micro apps or mu apps. This is help to control the network immediately. The apps control with both radio system and cloud. They use the smoothly called OpenAI Jimmy and which make easy to both smart and AI-based control apps. The also faster memory system called the riders, which is the storage live data. That way the apps can react quickly, keep getting the smart and over time. Here we have here the emulated the module. This is like a training ground of the micro apps. Before we use them, the real network we trust, we test the train here, and it supports the simple method like a base simulator is also advanced AI like reference learning. The emulator test as the safely train apps using the real or fake data. It work three strong. Office training, adjust and policy as need, and finally is run a real time at the network edge. It connected directly the radio network and make faster direction and less than the microsecond. It used the faster messaging system like a 0MQ and talk between the apps and cloud. The emulator also helps the run training the real world performance by the simulator and full network. Even without the funny hardware like without any fancy hardware like GPUs, is still performance gate and can handle up to the 100 users. Here we can see will be the aids performance. The result show the real time control using the micro apps work smooth better than sure cloud-based system. For example, video streaming because it's smoother and see the better speed. Even the movie streaming like a car or the AI module learn the faster working with the different condition. Also, here the system get the feedback for this app like a video buffering. It can the react and make things smooth for the user.